So when we're looking here, right, at our geostationary satellites, right, a geostationary satellite is really one that orbits the Earth at a specific altitude, right? So let's just enable the path here, right? So we're orbiting the Earth at a specific altitude, right, and it remains fixed over a single point on the equator, right? So it remains fixed. So as the Earth rotates, it just remains sit on that entire location, right? So its orbital period must be equal to the Earth's rotation, right? So we're looking at that. So the altitude of such an object can really be found by setting the orbital period equal to 24 hours and then using an equation for circular orbits. All right. So how do we get that done? Let's have a look at an equation. All right. Give me a moment. Let me just share my entire screen with y'all, and then we could get there. One moment. Let me share everything. Alrighty. So let's have a look here, right? So we're talking about the geostationary satellite, right? And we know that it stays at a fixed area, usually about the equator, right, for around 24 hours. So we set the period for of it staying there, right, to like 24 in order to figure out um the altitude, right? Or we tend to use that to figure out the altitude, right? So for such an altitude, it can be found by setting the orbital period equaling 24 hours. So let's look at the equation, right? Remember the equation that we got up here? This equation here? Yeah, we're going to be using this equation, right? Well, not this one, but like this one above it. My bad. So we're going to be using this equation. Alrighty? So remember, everything that I'm doing really comes from something else we've done. So using that equation, we can state now that m is equal to v squared over r, the radius of the geostationary satellite, rgeo, which is equal to g m of the Earth times another mass, right? R squared geo of the geostationary satellite squared, right? So looking at that, right? So the orbital speed, right, which is v, is going to be equal, right? We're gonna look at the equation, right? So the orbital speed v for geostationary satellite is related to its period, right? So how do we get that? That is gonna be now equal to 2 pi r geo over t. So we're looking at the angular velocity, right, of the entire thing. Remember the circle that we were talking about, right? If this satellite were to start at A, go all around and return to A, right, that would be 2 pi radians, right? Remember 180 degrees is going to be pi radians. One full revolution is going to be 2 pi, right? And then T here stands for the period, all right? So we're looking at that there. Hopefully that makes sense. Alrighty. So substituting into the equation and solving for the radius, right, or the altitude that we're looking at here. This is distance from the Earth, right, of the geostationary satellite, right? The orbit will be approximately three. This will be 35,786 kilometers above the Earth's surface. If we were to make T 24 hours, right, and then solve for our geo, right, we're gonna get us a distance, right? But we're not really here to solve for that distance. I'm just using these equations to help you guys figure out what we're talking about with geostationary satellites and the altitude, right? So we're just looking at that. So we can compare with other different orbits, our low Earth orbit satellites, right? So this is the last concept that we're looking at for motion. So we're looking at low Earth orbit satellites, right? Or what we call LEOs, versus or geostationary satellites, right? So low Earth orbit satellites, right, such as those used in GPS, or an example could be a global positioning system satellite, so GPS, right? Looking at that. So those are the GPS satellites orbit at a much lower altitude. So those altitudes tend to be around 200 to around 2,000 kilometers, right, above the Earth's surface, and their orbital period, right? So the orbital period, they tend to be around 90 to 120 minutes. Alrighty? So these satellites move quickly across the sky from the perspective of a ground observer. So they look like they're moving really, really fast, right? But if we were to look at our geostationary satellites now, satellites, LITs, right? So don't mind the spelling and stuff like that, right? Just looking at that, our geostationary satellites, right? For the geostationary ones now, these are ideal for things like telecommunication, right? So we know telecommunication, right? So telecom systems, right? So like we use them for telecommunications, we use them for weather monitoring as well, right? And for broadcasting. So you know those TVs with the antennae, right? That get the radio signals. Those would be coming from geostationary satellites, right? So we use them for that, right? Because they remain over a fixed position. So we use them for these because they remain over a fixed position, right, on the Earth, making them useful for continuous coverage over a specific area. So for example, our phone towers, right, are picking up signals from satellites, right? That geostationary satellite is fixed over, let's say, a region, the Caribbean, right? So any signal that is coming from that satellite that is over the Caribbean, right, that stays over the Caribbean perpetually, right, we can use that for cell service, right? So communications. We can use that to monitor the weather systems in the Caribbean, which are really important as it relates to the current climate crisis, right? And for broadcasting. So when I'm in Jamaica, so TVJ, CVM, those type of things, right? It helps with those types of coverages, right? When we talk about our geostationary satellites, right? Not really our GPS mechanisms, all right? So our GPS mechanisms are much lower orbit compared to our geostationary satellites, already. So those are really the main concepts to cover for the rest of this topic, right? So if we were to go back here now, right? So we're just here looking at this. So remember, our gravitational force is always acting on our object, right? So the blue arrows show our gravitational force, and there's always a velocity going outward, right? So remember when we talked about apparent weightlessness, right? So it's actually the object is actually falling continuously towards the Earth, right? But because of its orbital speed or orbital velocity, right, it tends to continue to miss the Earth, right? And it moves in this circular path, all right? So really and truly, that is what we're here to cover. That is the end of motion.